In this problem, we're told that we have water on the phase diagram marked by the blue X. That's right there. So a phase diagram is like a map that helps you navigate through the phases of a substance, depending on its pressure and conditions of temperature. Let's label the phases. There's your solid phase, there's your liquid phase, and there's your vapor phase for water. Now this problem is asking you, is there a way to boil water without heating it up? There certainly are. In fact, we showed you 3 demonstrations in class where we boiled water without heating it up. In order to boil water, you have to go from the liquid phase, cross this green line that I'm highlighting, and into the vapor phase. That's called boiling, liquid to gas. There's infinite places you can cross this line. The most obvious way is to increase the temperature. So at this X, if you go right, you will eventually cross that green curved line separating liquid from gas. But the question is asking, can you cross that line without increasing the temperature? So one of the answers is by simply decreasing the pressure, which is on the y-axis. From this X going down, we'll cross from liquid to gas, the boiling point. Some of you said increasing the pressure will boil water. That's incorrect, because if you're starting at this X and you go up and you're getting farther away from this line here in green, which represents all the boiling points of water. Now others of you said you can cool water to boil it. Cooling water is going left on this phase diagram. And if the only thing you do is cool water, that water is going to freeze. This is ice for water. So the question is asking, how do you boil water? Not how do you freeze water. Now in class, we did show you how to boil water by cooling it down first. Now you can cool water, but at some point, you're going to have to go down and again, cross this curved line. Now this problem, boiling happens when the vapor pressure equals the external pressure. Some of you said temperature. How can temperature equal pressure? They're 2 different dimensions. That's like saying distance is equal to time, or weight is equal to height. Next question. What temperature? So now you got to answer the question. Some of you didn't even give me a unit of temperature. You gave me a unit of pressure. And some of you didn't give me units at all. You just gave me a number. So I was asking, what temperature is the vapor pressure of water? 600 millimeters of mercury. So vapor pressure here is labeled on the y-axis. Let's go to 600. Let's see where it crosses the vapor pressure point. So it crosses right there. If you look at the increments given here, between 80 and 100, there's 4 increments. So that's 90, and that's 95. So the answer should be between 90 and 95. Now, it can't be 90 because this purple dot is at 90. It should be greater than 90. And if you take a closer look, it's before 95. But if you said 95, I give you the credit. But you can't say 90 because that purple dot is clearly before where it crosses 600. So acceptable answers were greater than 90 degrees Celsius all the way to 95 degrees Celsius. Next question. We're asked to estimate the boiling point of diethyl ether at standard atmospheric pressure. So again, boiling point is where the vapor pressure, and this whole data table gives you that information, is equal to the atmospheric pressure. And we're told at standard atmospheric pressure is 101.3 kilopascals. So when do numbers on this table equal this? That's the definition of boiling point. And we only need to consider the last row because it's asking about diethyl ether. All right, well, 101.3 is somewhere between 58 and 122. So that is when the vapor pressure equals the atmospheric pressure. That's how we define boiling. Boiling point is the temperature. So your answer should have units of Celsius. So an acceptable answer is between 20 degrees Celsius and 40 degrees Celsius. It shouldn't be 20 and it shouldn't be 40 because 101.3 is between these two vapor pressures. People in high elevations, like mountainous regions, live in an environment where there's less air. And if there's less air, the air pressure is going to be less than the standard air pressure at sea level. At sea level, the air pressure, or the atmospheric pressure, is about 1 atmosphere pressure. So on a mountain, it's going to be less than 1 atmosphere pressure. They will never boil water at 105 degrees if their pots or their boiling water is left to the open atmosphere, because by definition, the boiling points of liquids, such as water, is when the vapor pressure of that water is equal to the atmospheric pressure, which is called the external pressure. If this is low, then water will always boil at a lower temperature, because that's when the vapor pressure matches the external pressure. So to increase the boiling point of water at high elevations, you have to find a way to increase the external pressure. So you can increase the pressure above the water using a pressure cooker or something like that. The first option is wrong, because no matter how much heat you add, if there's not a lot of air pressure above that liquid, that water will simply boil faster, because it will never need to reach a higher temperature to overcome the atmospheric pressure, which is lower. Heating the water more gradually is not going to change the boiling point. The boiling point is defined there. In order to change the boiling point, you've got to change the vapor pressure and the external pressure. Decreasing the pressure above the water. If you remove even more air, that means the required vapor pressure is going to be even lower. So water is going to boil at an even lower temperature. Temperature measures the average kinetic energy. And if all these have the same temperature, they each have the same kinetic energy. Like your thermometer doesn't care whether you put the thermometer in ice, in air. It doesn't care about that. It only cares about measuring average kinetic energy. And if all the temperatures are the same, then they're all going to have the same average kinetic energy. If you have an open container of a liquid, those particles at the surface that have enough kinetic energy are going to leave the liquid phase into the vapor phase. That's called evaporation. If this is rate and this is time, this blue line represents the rate of evaporation. It's constant. Now, in an open container, there's minimal condensation, because if this is open, the wind is going to blow those evaporated particles away. They're going somewhere else, and this liquid is going to continue to evaporate until it dries up. In a closed container, this changes, because at some point, these evaporated particles are going to create what we call vapor pressure. They're going to collide with each other, and some of these particles are going to lose kinetic energy and return back to the liquid phase. That's called condensation. Initially, the condensation rate is low, because you got to wait until the vapor pressure builds up. But once the vapor pressure is constant, the rate of condensation will equal that rate of evaporation. And that marks the point of dynamic equilibrium. So in a closed container, dynamic equilibrium can exist. It can't exist in an open container, because the evaporated particles are constantly leaving. We just explained why that choice is wrong. And the first choice is wrong because evaporation is going to happen at the same rate. That's just dependent on the temperature and the intermolecular forces of the substance. Next question, we're asked to compare intermolecular forces with vapor pressure. Now, things that have a high intermolecular force, that means they're attracted to each other. They're not going to want to go from a liquid to vapor phase, or even a solid to vapor phase, because they are attracted to each other. So they're going to have a low vapor pressure, because you need gas particles colliding to cause vapor pressure. So they're inversely related. Now, the Lewis structures of these two substances are identical. So the main difference are these terminal atoms, sulfur versus selenium. They're both group 16. Selenium is lower on the periodic table, so it has a higher mass. In other words, it has greater London dispersion forces. Carbon diselenide is going to have a higher intermolecular force, and therefore it's going to have a lower vapor pressure. You have a container with some liquid. Those particles at the surface with enough kinetic energy to overcome its intermolecular forces are going to evaporate. And because the particles with the greatest kinetic energy are leaving, the average of the remaining particles are going to decrease. These particles that are leaving are absorbing energy to evaporate to a higher energy state. So evaporation and boiling are endothermic processes. They cool their surroundings. In this problem, we're asked to compare the boiling points, and we're given the structures. All three of these have similar molar masses. They're about the same size. So London dispersion forces are not going to be a factor. Instead, you need to consider the intermolecular forces. Hydrogen bonding is going to be the strongest intermolecular force in molecules, followed by dipole forces. In other words, is the molecule polar or not? Finally, we have London dispersion forces. And since London dispersion forces are primarily determined by the size of the particles, we're not going to consider them because all three of these are about the same size. Ethanol can form hydrogen bonds because it has a hydrogen directly bonded to an oxygen. Ethanol is going to have the highest intermolecular forces. Therefore, it's going to have the highest boiling point. Students sometimes think that a molecule that simply has a hydrogen and an oxygen anywhere in the molecule believe that they can form hydrogen bonds. That's a misconception. The hydrogen has to be directly bonded to an oxygen, fluorine, or nitrogen. But it does have an area that is polar. So acetone has dipole forces. It's going to have the next highest intermolecular force. Therefore, it's going to have the next highest boiling point. Finally, propane cannot form hydrogen bonds with other propane molecules, is not polar, so the only thing it has is London dispersion forces, which are the weakest forces pound for pound. So because propane has the lowest intermolecular forces, it's also going to have the lowest boiling point. So substances with high intermolecular forces, as we said multiple times already, is going to have a low vapor pressure because it's not going to want to vaporize because it's strongly attracted to each other. And therefore, it's going to require greater temperatures to bring that to a boil in order for the vapor pressure to match the atmospheric or the external pressure. So it's going to have a high boiling point. Or you can say substances with low intermolecular forces are going to vaporize easier because they're not attracted to each other. So they're going to have a high vapor pressure, and therefore they're not going to require high temperatures to boil. They'll have a low boiling point. The triple point of a substance is where three phases meet. In this case, solid, liquid, and vapor. They all meet right there at point A. So point A is described with 0.0060 atmospheres and 0.01 degrees Celsius. What is the physical state of methanol at a temperature near ice water? Well, ice water is near 0 degrees Celsius. And we need to consider the second row because that's the data with methanol in it. So melting point separates solid from a liquid. And boiling point is the boundary between liquid and vapor. And because 0 degrees Celsius, because it's ice water, is between negative 97 and positive 64, methanol is a liquid. Volatility describes how easily a substance evaporates. A substance will evaporate most easily if it has low intermolecular forces and therefore create the greatest vapor pressure. So no matter where you look on this graph, the substance with the greatest vapor pressure is chloroform. Therefore, chloroform is the most volatile. This diagram, we have two manometers. The difference in the level of the mercury tells you the vapor pressure. In manometer A, you can see there's more pressure, more vapor pressure from this liquid pushing the mercury. So A has a greater vapor pressure. One way to increase vapor pressure is to increase temperature, because those particles in the liquid will have greater kinetic energy to vaporize. And finally, which experiment crosses the normal boiling point? Boiling happens when you cross from the liquid phase into the gaseous phase. And that can happen at infinite points along this curve between the liquid and gas. But the normal boiling point occurs at 1 atmosphere, and that's a single point. That's this point right here. I'm circling in light blue. So only one experiment crosses this blue dot, and that's experiment 1. Now some of you said experiment 2. This is not a boiling point. That's called sublimation. Boiling point is liquid to gas, not solid to gas. Experiment 3 doesn't cross this blue dot. This blue dot represents the only single normal boiling point for water. It looks like this is water. Experiment 3 crosses the triple point, not the normal boiling point. Experiment number 4 doesn't cross any boiling point. Experiment 4 is occurring above the critical point. And above the critical point, there's no clear boundary between the liquid and gaseous phase.